Welcome to the second part of matrix formulation of quantum mechanics. So in the second part of matrix algebra, let us discuss few other things about matrix algebra. So now let me define first of all that is what is a determinant. So determinant is defined as this way or this way, and if A is a square matrix, then its determinant can be written as and to find its value, we expand this along any one of the row or the column. So let us expand it along first row, that means the determinant, it will become first element minus 1 raised to power the sum of these two quantities, so it is 1 plus 1, means these are the indicator of rows in the column, in which row and in which column they are sitting. And so along this I will delete this row and this column, and I will write down this remaining part here. So it is A22, A23, A32, A33 plus A12 and minus 1 raised to power 1 plus 2, this one and this two, right? Then now omitting this column and this row, and remaining will be this and this. So I will write down it here. Plus A13 minus 1 raised to power 1 plus 3. In the similar manner, I will omit this row and this column, so remaining part will be this one. So A21, A31 and A22 and A32, right? So that's what I am getting here. Now I will expand it, or I will simplify it. So it is A11 and minus 1 raised to power 2, it's again positive quantity, and now this is multiplied by with it and minus of this, so it is A22, A33 minus A32, A23 plus, sorry, not plus, but here it is minus 1 raised to power 3, so it is negative. So A12 fit with it and this, so it is A21, A33 minus A31, A23 plus A13, A21, A32 minus A31 and A22, like this. So this is the value of this determinant, and these quantities, this is known as minor of the first, this element. This is also known as minus of this element, and this is also known as minor of this element. So that means The equation can be written as a11 minus 1 raised to power 1 plus 1 and minor of this element plus a12 minus 1 raised to power 1 plus 2 minor of this element plus a13 minus 1 raised to power 1 plus 3 minor of this element, and it can be written as this whole of the quantity is known as the cofactor of this element. Let me call it as C11, and this is also known as cofactor C12, and this is also known as cofactor of this C13. So that means this is A11 C11 plus A12 C12 plus A13 C13. So this is a way that how this minor and cofactor can be defined, and in terms of minor and the cofactor we can find out the determinant of a matrix. So that means Mij is known as minor of ijth element, and Cij is known as cofactor of Aij, and Cij is nothing but is equal to minus 1 raised to power I plus j and Mij. So therefore determinant can be written in general form. Determinant of a matrix A is equal to summation j is equal to 1 to n Aij and Cij, and I have defined that how Cij can be written. Now let us define minor. Minor of the element Aij is the reduced determinant of A obtained by deleting the ith row and jth column of determinant A, and the order of minor is n minus 1, right? Also, there is a very important property that determinant of product of matrices is the determinant of first matrix or the determinant of second matrix, or it can be written in another way as the determinant of BA, right? So this is all about determinant of a matrix. Now I will talk about complex conjugate of a matrix. So consider a matrix whose elements are complex numbers So that means it's defined as A is equal to A11 plus iota V11 plus A12 plus iota B12 A13 plus iota B13, then A21 plus iota B21, A22 plus iota B22, A23 plus iota B23, A3 plus iota B31, A3 plus iota B32, A33 plus iota B33, then its complex conjugate is defined as complex conjugate of every element. A star is equal to A11 plus iota B11, its complex conjugate, A12 plus iota B12, its complex conjugate, A13 plus iota B13, its complex conjugate, then A21 plus iota B21, its complex conjugate, A22 plus iota B22, its complex conjugate, A23 plus iota B23, its complex conjugate, A31 plus iota B31, and A32 plus iota B32, its complex conjugate, A33 plus iota B33, its complex conjugate. And if I take their complex conjugate, then this can be written as A11 minus iota B11, A12 minus iota B12, A13 minus iota B13, A21 minus iota B21, A22 minus iota B22, A23 minus iota B23, A31 minus iota B31, A32 minus iota B32, A33 minus iota B33. In general, if a matrix is defined as Cij with m is to n order, then its complex conjugate is the complex conjugate of every element. This is that how we will define a complex conjugate of a matrix. Then next, let us talk about transpose of a matrix. Transpose of a matrix. So if rows and columns of a matrix are interchanged, the resultant matrix is called transposed matrix. And let us define it mathematically. So that I am having a matrix A11, A12, A1n, A21, A22, A2n, and so on, AM1, AM2, and so on, AMN, then its transpose is defined as either with AT or A prime or A tilde. is A11, A12, sorry, it's transpose means I have to exchange the rows and the columns. So in place of rows, I have to write down this column. So it is A21 and so on, AM1. Now this as a second row. So A12, A22 and so on, AM2 and so on. This can be written in other way. So it is A1n, A2n and AMN. So this is a way that how it can be written. And in short form, this transpose of it can be written as Aij, its transpose M is to N can be written as Aji with order interchange. So it will become N by M. And there is a very important property which we will use in later. So the property is that we are having a product and it will if we will take their transpose, then it is the transpose of B first and the transpose of A. Right. So this is a very important property which we have to keep in mind. Then let us talk about Hermitian conjugate matrix. Let's talk about the Hermitian conjugate matrix. So when two operations of complex conjugation and transposition are carried out one after another, on a matrix, the resultant matrix is called Hermitian conjugate of the original matrix. Conjugate of the original matrix. And denoted by a dagger, right? So this symbol is known as dagger and we call this quantity as a dagger. So let us take it, or let us consider, or let us understand it by taking some example. So given a matrix A, and this matrix is given as A11, A12, A1n, A21, A22, and so on, A2n, and AM1, AM2, and so on, AMN. Now I have to take or apply two operations. So let us apply on it a first operation. Take its complex conjugate, and its complex conjugate can be defined as A11 star, A12 star, A1n star, A21 star, A22 star, and so on, A2n star, AM1 star, AM2 star, and so on, AMN star. Now, if I take its transpose, then it is known as a dagger, and the resultant matrix which I am getting is given as basically it is A11 star, A21 star, AM1 star, A12 star, A22 star, and so on, AM2 star, and A1n star, A2n star, and so on, AMN star, right? So this is a dagger, and I can also do one other thing, that if I take a transpose here, then its transposes can be written as A11, A21, AM1, A12, A22, AM2, and so on, A1n, A2n, AMN, and if I take its complex conjugate, it will become a dagger, and it can be it again will become this matrix, right? So we can apply two operations simultaneously. Every operation can be applied first and then second, and vice versa. So then what I am concluding, that this a dagger is equal to a star t or a t star. Both are equal, or in other words, I can say that aij, its dagger, and it is this order matrix, then it will become aji star, and it is n cross m. So that's it. Now let us try to understand this by taking an example. So let us take an example. So for a given matrix A, write down A star, A T, and A dagger, right? So let us consider a matrix A, and it can be written as 2 plus 3 iota, 1 minus iota, 5 iota, 3. Then it is 1 plus iota, 6 minus iota, 1 plus 3 iota, minus 1 minus 2 iota. It is 5 minus 6 iota, 3, 0, and then minus 4. So let us try to find out complex conjugate is 2 minus 3 iota, 1 plus iota, 5 iota with negative sign, means all the terms having iota, their iota will be changed to minus iota. It is 1 minus iota, 6 plus iota, 1 minus 3 iota, minus 1 plus 2 iota. It is 5 plus 6 iota, it is 3, 0, the negative sign, minus 4. Now I can also find out transpose. So it is transpose of this means 2 plus 3 iota, 1 plus iota, 5 minus 6 iota, and then it is 1 minus iota, 6 minus iota, 3, then 5 iota, 1 plus 3 iota, 0, it is 3, minus 1 minus 2 iota, minus 4. Now a dagger, either I will take its transpose or I will take complex conjugate of this. So I will take its transpose. So its transpose is basically, so it can be written as 2 minus 3 iota, 1 minus iota, 5 plus 6 iota. It is 1 plus iota, 6 plus iota, 3 minus 5 iota, 1 minus 3 iota, it is 0, it is 3, minus 1 plus 2 iota, it is minus 4. So this is a dagger. So this is a way that how things can be calculated. Now there is a very important property which we have to keep in mind, that is AB, its dagger is equal to B dagger and A dagger, right? So now I will talk about next symmetric and antisymmetric matrix. Symmetric and antisymmetric matrix. So a matrix is called symmetric. It's called symmetric if transpose of a matrix is equal to its original form. That is, we can say that Aij is equal to Aj and is said to be antisymmetric or skew symmetric if the transpose is negative of original matrix, or in other words I can say that Aij is equal to minus Aj, then it is said to be antisymmetric matrix. Then next is a very important, that is Hermitian and anti-Hermitian matrix. I am simply recapitulating these results. I am not talking about in more detail. Hermitian and anti-Hermitian matrix. So a matrix is called Hermitian is called Hermitian. If a dagger is equal to its original, or AJI is equal to AIJ, and is said to be anti-Hermitian or skew Hermitian, if a dagger is equal to minus of A, or I can express it as AJI, complex conjugate, is equal to minus AIJ. And there is a very important property. What was that? Every square matrix can be uniquely written as sum of A Hermitian and an anti-Hermitian matrix. That is, mathematically, this can be written as, if B dagger can be expressed as A dagger plus A divided by 2, and then it must be equal to B, and similarly C dagger can be expressed as A dagger minus A divided by 2, then it is equal to minus of C. So it is a property of a Hermitian, and it is for the anti-Hermitian, right? Then next is a property, or the next matrix we will define as normal matrix. A matrix which commute with itself, a matrix which commute with its own Hermitian conjugate is said to be normal matrix. Mathematically, if A dagger is equal to A dagger A, then we can say that A dagger minus A dagger A is equal to 0, or in other way I can write it in the form of a commutator, it must be equal to 0, right? So then this is said to be a normal matrix. Then let us talk about the very important thing, that is the trace of a matrix. The trace of a square matrix A is equal to Aij is defined as the sum of its diagonal elements. elements. It is also called spur or diagonal sum. So that means trace of a matrix or the spur of a matrix can be written as, and it is summation I is equal to 1 to n and aii, means sum of all the diagonal elements. And its property, that a very important property, that trace possesses the cyclic property. What does that mean? That if we are having a product of matrices in this order, then their trace of their product can be written in this form, then that must be equal, right? So here I have written A here, right? So that's the meaning of its cyclic property. Then let us define inverse of a matrix. Inverse of a matrix. If there exists a matrix B, matrix B such that A dot B is equal to I, or B dot A is equal to I, then B is called inverse of A, that is A inverse. And the inverse of a matrix can be calculated as A inverse is equal to 1 over determinant A and transpose of cofactor matrix, where AC represents the cofactor matrix. And this equation suggests that A inverse exists if determinant of A is non-zero, right? Then let us talk about orthogonal matrices. Orthogonal matrix. A real matrix is termed as orthogonal if its transpose is equal to its inverse. That is, A inverse is equal to A transpose, or I can write down it as A transpose is equal to identity matrix. Also, we know that the determinant of A is equal to determinant of A transpose Now consider the equation A transpose is equal to I, and taking determinant on both sides, so determinant of A transpose is equal to determinant of I. So it is determinant of A, and determinant of A transpose is equal to determinant of I, and it is determinant of A. If I use this property here, then it will become determinant of A, and determinant of I is 1. Determinant of identity matrix is 1. That means determinant of A spot square is equal to 1. That means determinant of A is equal to plus minus 1. So that means this is another property of orthogonal matrix. This is property of orthogonal matrix, right? Then let us talk about unitary matrix. So a matrix, and it may be a complex matrix. So a complex matrix is said to be a unitary if U inverse is equal to U dagger, or you can say that U dagger is equal to U dagger U, or it is equal to I. Also, there is a property which is known to us, that is determinant of A dagger is equal to determinant of A. I will use this. So that means if I take determinant on both sides, so from here I can write down as determinant of U dagger is equal to determinant of I, or you can write down it as determinant of U and determinant of U dagger is equal to 1, and here U dagger is simply equal to U using this property. So that means determinant of U its mod square is equal to 1. Now U is a complex number. U is a complex. So that means determinant of U may be a complex number. It is a matrix and its determinant will be a complex number. So that means determinant of U its mod square is equal to 1. This is possible if and only if determinant of U can be expressed in the form of exponential of iota theta, and determinant of U dagger can be written as exponential of minus iota theta. Right, so this is possible if and only if I can express it in this form, right? So this is another very important property of unitary matrix, right? So thanks for watching this lecture. In the next lecture, I will talk about another important properties relating to, or important things relating to matrix algebra.